What if the very foundation of our understanding of the universe's expansion is flawed?
The Hubble tension, a perplexing discrepancy in measuring the universe's expansion rate, might just be resolved by re-evaluating our reliance on supernovae as cosmic yardsticks.
But here's where it gets controversial. Could our long-held assumptions about these standard candles be leading us astray? In a recent exploration of cosmological models, new data has challenged some aspects of our understanding, though it doesn't dismantle the Big Bang theory or the concept of an expanding universe. Instead, it points to a potential flaw in our calculation of the Hubble constant, a value central to describing this expansion. This isn't entirely surprising, given the existing Hubble tension, a disagreement between different methods of measuring the universe's expansion rate. To grasp this, let's step back to the early 20th century. In 1929, Edwin Hubble, building on Henrietta Leavitt's work, discovered that galaxies farther away from us exhibit greater redshifts, indicating a linear relationship between distance and redshift. This led to the proposal of the Hubble constant. Around the same time, Einstein had introduced a cosmological constant to his theory of general relativity, initially to support a static universe. However, Alexander Friedmann and Georges Lemaitre independently showed that this constant could also describe an expanding universe, a concept later solidified by Howard Robertson and Arthur Walker with the Friedmann-Lemaitre-Robertson-Walker (FLRW) metric. The FLRW metric, which forms the basis of the standard cosmological model, lambda CDM, incorporates the cosmological constant, lambda, and the Hubble constant, h0. While related, these constants are not identical. The expansion rate is influenced by dark energy, represented by lambda, dark matter, regular matter, and their distribution.
Matter acts as a gravitational pull, while dark energy pushes everything apart, creating a dynamic balance that determines the expansion rate. Interestingly, the early universe, being denser, should have expanded at a slightly slower rate. However, the discovery of an accelerating expansion revealed the presence of dark energy and solidified the importance of the cosmological constant.
This is why the Hubble constant is often referred to as the Hubble parameter today. For decades, the lambda CDM model was supported by observational evidence. However, recent measurements of the Hubble parameter have introduced inconsistencies. The three primary methods for determining this parameter, distant supernovae, the cosmic microwave background, CMB, and baryon acoustic oscillation, BAO, yield conflicting results. Supernovae suggest an expansion rate of 71 to 75 km/s/mpc, the CMB indicates 67 to 68 km/s/mpc, and BAO measures 66 to 69 km/s/mpc. This discrepancy is the Hubble tension. One might assume the supernovae measurements are at fault, but the issue is more nuanced. Each method relies on specific assumptions and models, and even alternative techniques like gravitational lensing and astronomical masers produce conflicting results. This is where the new study becomes intriguing. The research suggests that accounting for the age of host galaxies in supernova measurements could significantly reduce the Hubble tension. By comparing supernovae in galaxies of similar ages, regardless of their redshift, the team found that the expansion rate estimates align more closely with those from the CMB and BAO. However, this finding is preliminary, based on a small sample of about 300 galaxies. The upcoming Rubin Observatory, set to come online soon, promises to expand this dataset dramatically, potentially confirming or refuting this new approach. If this model holds, it could mean rethinking the cosmological constant as the sole source of dark energy. But is this the end of the story, or just the beginning of a new chapter in cosmology? What if the solution lies not in one method but in a synthesis of multiple approaches? And this is the part most people miss: the universe might be far more complex than our current models suggest. What do you think? Could this new perspective resolve the Hubble tension, or are we missing something even more fundamental? Share your thoughts in the comments. Let's spark a cosmic debate.